Madeleine. I'm one of the hosts, and I will directly leave the floor to you, Stefan, to start this webinar. Most welcome, everyone.
Thank you, Madeleine. And very welcome to this webinar on metal and polymer component manufacturing. Well, this one specific on the topic of iron melting process and slag formation mechanisms, which is our first webinar in a series in a module called ferrous metals. I think there will be 5, 6, or maybe 7 webinars on that topic, but we have a lot of other topics as well and modules. You see the participant list for those registered. If maybe someone missing being a late registrant, but as you see, we have visitors or participants from all over the world. And that is pretty fun to see. Even though we market mostly towards Sweden, we get participants from everywhere. Quite a lot from India are registered today, and that's fun. So welcome. The Webloom project, maybe you've already read something about it since you managed to register for the project, but it is a project where we receive funds. The School of Engineering, that is, here at Jönköping University, receive funds from the KK Foundation in Sweden to create quick, effective competence development packages for the metal and polymer industry at the advanced level to help the companies to get a quicker innovation, improving product quality, and raising their competitiveness and readiness when the crisis is over. And next, Made, if you...
It's some things.
It got stuck.
It got stuck. Yeah.
Well, the one you are looking at now, or hearing at least, that's me, Stefan Berlin, a project manager here at the School of Engineering, and my colleague Madeleine Zetterlind of mine, which you will meet more later on towards the end of the webinar. But our main characters are, of course, the presenters, which is Lucian Diacono here at Jönköping University.
Hello.
Our researchers. And then we have our industrial guests, Rutger Gyllenram from Kobolda and Partners, and then Johan Ekengård from FE Induction. It will be very interesting to listen in on your industrial experience on this topic. And then, just to give you a short brief of what's coming up. So, intro, we are almost through. The presentations will begin in more or less a minute. And after a while, we will divide us into discussion groups, where we'll have 2 different focuses in each discussion group. And then after about half an hour, we will have a short wrap up before ending. So all in all, 1.5 hours, since these are the Central European time zone that is published on this one. It may be irrelevant for most of you. So please, do have your microphones turned off during the presentations. If you have questions, which are most welcome, do write them in the chat. Either you write them to everyone, or you write them to me, and I will keep track of them. That is, address them to Stefan Brolin in the chat. And please be active in our group discussions towards the end. The webinar will be recorded, so and will be available to you afterwards. And if you don't want to be seen in the webinar, turn your camera off. But in the discussion groups, please turn on your camera to make the communication easier between us. And If you're unfamiliar with Zoom, you have the buttons down below. Far left, you have the microphone on or off, the camera on or off, and then you have the chat function, which opens a chat window where you can choose whom you send the message to. And that is about it. And by that, I welcome Lucian to take over.
Yes, so welcome everyone. And Madeleine, please let's go to the next slide. As Stefan mentioned, this is the first webinar within a series dedicated to the ferrous metals, and within this series, the next webinar will be about the molding materials, will be a webinar about the metal penetration, and finally, at the beginning of the summer, about the metallography of cast iron, and another webinars are planned for the end of the year and also in the spring of 2022. Yes, but let's start with this webinar, and finally what we need to have when we are doing melting. So these are some of the steps: preparing the metal and loading the furnace, melting the metal, refining and treating the molten metals. So by this, we introduce some elements to purify. We may adjust the molten bed composition, and also by adding elements, we may affect the nucleation and also the growth during solidification. Another step is holding the molten metal, taping, and finally transporting the molten metal to the point of use and to keep the metal in molten state until it is completely poured. The next slide is about an important factor to decide when using the melting unit. And finally, these factors are related to the temperature required to melt the alloy, the melting rate, and the quantity of the molten metal required, the economy of installation, and the last factor is the environmental and waste disposal requirements. Within the ferrous alloys, the furnaces used for melting are cupola furnace, the induction furnaces, and the electric arc furnaces. And related to the electric arc furnaces, their usage increased in the last years. When speaking about cupola furnace, this is, yes, Madeleine, the next slide, please. Yeah. So when speaking about cupola furnace, we have a few zones within the cupola furnace: the well, that is at the bottom part, the combustion zone, also called the oxiding zone. And as you see in this zone, there are a few reactions that take place in this zone. We have the reducing zone, and within this zone, the charge is protected against oxidation. Finally, we have the melting zone, a preheating zone, and the upper part of the cupola furnace is represented by the stack zone, and it provides the passage to hot gases to go to atmosphere from the cupola furnace. Next slide. Within the cupola furnace, there are some operations. First of all, to prepare the refractory lining, that is very important. Finally, the lighting and burning in the coke bay, the charging that consists of metal, alloying ingredients, limestone, and so on. The metal charge may consist of pig iron, cast iron scrap, steel scrap, and also returns. The first operation within the cupola furnace is the melting, finally the slagging and the taping, and the last is dropping down the bottom, and by this the metal is poured from the furnace. Yeah, some of the advantages of the cupola furnace, it's simple and economical to operate. So it has quite a low cost of melting. Cupolas can refine the metal charge by removing the impurities out of the slag. Cupola furnaces are more efficient and less harmful. High melt rates is easy to operate. The temperature control is adequate. Finally, the chemical composition may be controlled. And not the last is the efficiency of cupola that may vary from 30 to 50%. At the same time, some limitations and disadvantages. It may be the chemical composition, even if it was presented like an advantage. There are some limitations, and certain elements like silicon, manganese are lost, and the sulfur may be picked up. There is a close temperature control, and finally the metal purity. Next. The next is about the electric induction furnaces. That there is a furnace in which the heat is applied by induction heating of a conductive medium in a crucible placed in a water-cooled alternating solenoid coil. Yes, the process required within melting or with induction furnace are mixing and homogenization, not only of the charge, but also of the temperature, the intensive stirring at the melt surface, avoid of erosion of the ceramic lining, melt instabilities, and intensive stirring for cleaning of the melt. Related to the types of the induction furnace, there are coreless induction furnace, and this one is used mainly for melting, and according to the frequency, there are small frequency, low, and medium or high frequency induction furnaces, and the channel induction furnace that is used mainly for holding and is used in a duplex with the cupola furnace. Yes, the advantages and disadvantages of the induction melting. So a fast startup from cold, flexibility, natural steering, a better working environment, energy conservation, and the cleaner melting. And the disadvantages: lack of refining capacity, removal of sulfur and phosphor, and influence of the refractory lining. Yes, and in the next, you will see a video from a foundry.
Sorry, something happened here. Oh, here is the video.
Yeah.
I'm not sure we have time to play the video, Lucian. Maybe we should recommend to watch it later.
Yeah, so we are at Arvika Foundry, and we will speak about the melting process. We have here.
Maybe you can just say a few words about the video.
Yeah, within the video is possible to see about the induction furnaces used at the foundry, and finally about the charging process and how to control the chemical composition during the melting process.
Yeah.
This is the outline of the video.
Thank you, Lucian. And the last picture.
And in the last one is finally what we have at the university. So we have the possibility to do cast iron mainly due to the lining material. And we have an 80 kilos induction furnace. And also we tried to obtain compacted graphite iron with the help of a dispositive from Sintercast. And as you see in the slide, there are my contacts. So please, if you want to collaborate, just mail me. Thank you.
Thank you very much, Lucian. So let's move on. Thank you. And let's invite Johan Ekengård to on stage. Please, Johan.
Thank you. Can you hear me well now? Yes. Yeah. My name is Johan Ekengård, and I have a background as process metallurgist, trained at KHH in Stockholm, where I also, in cooperation actually with Jönköping University, finished my PhD in 2016. I've been working with metallurgy at Scana Steel, the Holm Tooling, Volvo Group Foundry, and also the last, until 1.5 years ago, I was 9 years at Sandvik Rock Processing in Svedala. Currently, I'm at the FE Induction as managing director of the Swedish subsidiary and technical responsible for material science issues and calculations and so on. We supply induction coils for different applications like annealing, hardening, post-weld heat treatment, and induction heated feeders also for castings. So maybe you have seen us at some conference before Corona entered the world. Lately, we also supply some welding services in Norway. So on the right on this picture, you can see the savings you can do with having an induction heated feeder instead of a nice exothermic or isolating sleeve. This is not possible on all feeders, but we are working on it. So we can take the next. So I will talk not so much about induction heating, but more about the metallurgy in the melting furnace. We'll tell you first about some tools I use in my daily work that I believe would be great for you too, and then some examples of use from my own research. So we'll dig somewhat deeper into these metallurgy issues. Many of you are in workshops with induction furnaces, I've seen, but I also know some of are running blast furnaces. So whatever the melting process, at least reactions between iron oxide, carbon oxide, and so on, silicon and manganese are involved in your daily operations. And some of you are much familiar with the tools I will talk about, but some of you might be new to them. So I hope it will be interesting for all of you. We can take the next picture. So we start with the iron carbon diagram. This is the basics that I use almost every day for different purposes. On the y-axis, you have the temperature, and on the x-axis the carbon content. So I've divided with the blue line here the steel and the cast iron areas in general. There are mixes in between as well, but so if we, for example, we can click the next. For example, a composition of 2.75% carbon, and we go from liquid and start to solidify this alloy. We will start solidifying at around 1330 degrees Celsius. In the diagram, it's not 1330 or 1340. It's hard to see there, maybe, but depending on alloy level of other alloying elements, of course. So the liquid at the solidification front will get an increased carbon content as temperature decreases. If you follow the red arrow on the most right red arrow there. And eventually the last solidified melt will have a so-called eutectic carbon composition at the lowest liquid area point, the 430% it says there, or 426, depending on which stability of the diagram you're looking at, but we will not go into that. And the solidified austenite, the left red arrow downwards will also increase its carbon content during solidification. So I will come back to this, but this is an important concept that the carbon content will increase during solidification, both for the liquid and for the austenite. So we can take the next slide. Another, in the iron carbon diagram, we had it's carbon that is in the focus, of course, but carbon is also very much influenced by oxygen in the melting process, and the stability and temperature dependence of formation of different oxides can be seen in the Ellingham diagram, where we have on the y-axis here, we have the driving force, delta G, of formation of the oxide, and for different alloys forming oxides then with oxygen. And it can be used for many important things. I will highlight, for example, the reactions. We can take the next click here. As you see with the red circle there, the magnesium oxide and calcium oxide are two of the most stable oxides in the whole metallurgical system, and they are very stable and therefore used in refractory, for example, but also as the oxidizers. Calcium in steel, for example, CASI or Sika wire addition during refining, or magnesium in ductile and the compacted graphite iron. So that's why they are used. And if we go to the next, we also have silicon and aluminum, of course, that are used as the oxidation agents in both foundries and steelworks, steel shops. So one kind of deviating line in this diagram is the carbon oxide line, and it is the slope is in the wrong direction, so to say. Or this is used very much to reduce other oxides. So if you look on the right of the diagram, where this red line carbon dioxide goes down with increasing temperature, you can see that above, for example, 1400, 1500 degrees, the carbon dioxide line is lower. That is more stable than, for example, chromium oxide or manganese oxide or silicon oxide even. So then you can use carbon to reduce this, for example, chromium oxide. It's very valuable to do that when you do stainless steel, because then you can save a lot of chromium that would otherwise be in the slag and lost. So this is the basics of the basic use of, in my world, of the Ellingham diagram. So we can take the next picture. You can take the next, Madeleine.
Yes, I'm trying.
Okay.
Sometimes it gets stuck now.
Okay, yeah. And and then we come to my favorite. A third important tool or visualization is the oxidation graph, where we have on the y-axis the oxygen content, and on the x-axis, on the y-axis oxygen content, and the x-axis time from addition of the oxidation agent. And this could be, as I mentioned before, aluminum or silicon or magnesium to be added in the melt. And then we get a rapidly sinking dissolved oxygen content in the melt because of these stable oxides that we use for the oxidation. And the dissolved oxygen content will then go down in the melt, and at the same time the total oxygen content will also decrease because we are removing and flotating the formed oxides in the melt. So the gray curve that I've strengthened with the red arrow is the line building up the formed oxides, and then they are removed. And I will also come back to this fact in the next pictures. So we can take the next. So I thought we could look at these equilibrium reactions a little more in detail from my own research. We performed a number of lamellar, compacted, and ductile iron melts, and then measured dissolved oxygen, chemical composition, temperature, and we took also slag samples for both for all these three main cast iron melt sorts, or what. So we can take the next picture. So the oxygen in the melt is can be measured using something called oxygen activity measurements, and it's a probe that you put into the melt, and the reading you get is called oxygen activity, and it's extremely temperature dependent, and according to this formula on the left here. And in the diagram you can see the measured oxygen activity for different cast iron versions. So we have the ductile iron in the bottom, the compacted graphite iron, and then the lamellar graphite iron to the top left in the diagram. So we get definitely different oxygen, measured oxygen levels in the different types of iron. We can take the next picture. What we also found was that this kind of fading or fading effect of addition of the oxidant. So in this diagram, you can see that we recalculated our oxygen activity readings to there was a researcher that in Belgium, Mampay, that worked with trying to get the temperature dependence away from the issue here, and then we recalculated the oxygen activity measures to constant temperature. And then we see that actually after addition, the dissolved oxygen content goes down very rapidly, but then after some time, it recovers again. And this could be connected to the flotation and removal of the inclusions in the melt. And then the magnesium in this case is not present as much anymore. And then the oxygen, dissolved oxygen recovers in the melt. So that's why you have to cast compacted and ductile iron in time before it's too late, so to say. So we can take the next picture. We also connected for the gray irons, we looked at, we extrapolated the oxygen, measured oxygen to the liquidus temperature. And then you can we found out that for different carbon contents in different lamellar graphite irons, then we get different oxygen levels at the solidification front, so to say, when it starts solidifying. So it could be connected to the iron carbon diagram again. So we have different oxygen levels for different graphite irons with different carbon contents. And this we believe that this is has to do with how graphite and austenite are growing at the solidification front. So the oxygen will impact that. So we can take the next slide. As a final connection, the relative slag content from our ductile iron experiments. And this is also connected to the Ellingham diagram, as I talked about earlier, or just some minute ago. And so the stable oxides are actually after time we turn off the furnace, so to say, and then the slag is growing and going the natural way, so to say, without any impact from anything. And then the stable oxides, they are growing in relative numbers, and the less stable oxides are decreasing in relative numbers. And you can see here that magnesium and aluminum oxide and calcium oxide are growing, and iron oxide and manganese oxide are decreasing in relative amounts. So we can take the next and last slide. So these refining operations I'm not working with daily anymore, but definitely I'm working with phase diagrams every day, and also the iron carbon and also the Ellingham diagrams and somewhat the oxidation, because we are in the welding business very much also, and the induction heating for hardening composition, hardening applications. And so this is some tools I use every day, and hope you got some inspiration to use them in your daily work as well. Thank you so much. And I will leave the word to Rutger to talk about the importance of scrap handling and control in metallurgical systems.
Thank you, Johan. I think that we have a raised hand from Muhammad. Perhaps we have 1 minute for that.
Yes.
Yeah, but one very small question. Like, I was just looking to, receive your comments about the non-equilibrium effects, both in equilibrium iron carbon diagram as well as in Ellingham diagrams. So, have you considered them, or just didn't consider them?
You mean that they are the non-equilibrium?
Yeah, the phenomena. I mean, the phenomena which is non-equilibrium as well as equilibrium both happens concurrently. So, have you sort of considered them?
It's definitely part of it's definitely part of the discussions of the results in our work. We have in the experiments we performed, we tried to get as much time as possible for the equilibrium to set in, but of course it's not we are aware of that it's not the equilibrium according to the diagrams, but the main principles still apply. So that's so yeah, I hope that's an answer to your question.
Thank you so much.
Thank you, and please keep all your questions for the discussion later. And now, Rutger, please, stage is yours.
Thank you, Madeleine. So I'm nice to be here after Lucian and Johan, and I'll try to continue in their spirit. But we do at Cobalder, we do raw material optimization, and we work together with Jönköping University in the training courses for teaching raw materials. And normally raw materials is perhaps not a big issue, but in times of change, it's really big issue. We can have a next slide. Next.
Sorry,
No problem.
Yeah, sorry. Oh.
So no, before what?
Yep. Sorry.
There, great. Yeah. So what we have now, we are in a time of change, and the change is the discussions and the industrial change depending on the global warming. And for the steel and metals industries, it's about decarbonization. For the big steel plants, it's a trend from going from the blast furnace, basic oxygen furnace, towards direct reduction and electric arc furnaces. So how will that affect the foundries? Well, we can think a little bit about what will happen to scrap. Well, when blast furnaces close down and replace the BOF shops with electric arc furnaces, starting to buy scrap on the open market, it will affect the availability of scrap and the availability of good scrap. Probably it will affect the price, making it more important to be able to buy the right quality rather than the one is offered to you. And of course, you might end up with being offered quality less than you are used to, or you'll be forced to buy super quality. I know, for example, powder companies, they often, or some do buy billets and cut them up in pieces just in order to get the right quality. I don't hope that will happen to these foundry industry, but scrap will definitely change. So what will happen with the direct reduced iron, HBI, hot briquetted iron. Well, it's normally used in electric arc furnaces. And if we look at the ideas that we have today about the amount of transition from DRI, from blast furnaces to direct reduction, we can see that there will be a shortage of very good DR pellets to produce DRI. And then perhaps the DR furnaces, the DR companies, they will start using more scrap in their mix. So there will be a huge pressure on scrap, perhaps not this year, perhaps not next year, but within the next 10 years. We can have a next slide, please. And when you look at the electric arc furnace, and you look at the slag formation in the electric arc furnace, you can see here from this slide that the silicon content in the DRI is really important for the economy. If you look at the picture to the left, if you don't match the silicon that goes in together with the direct reduced iron with lime and magnesite, MgO, then you will get an undersaturated slag. That means that you will consume MgO from the lining, and that's extremely costly. So if you have a poor DR pellet, you will get a rather SiO2 rich DRI, and then you will have huge slag amounts. To the right, you can see two examples, what happens in a 100-ton furnace when you have 20-ton scrap or 80-ton scrap. And you can see how much you save or lose when you go from 2% of silicon in the DRI to 4% of silicon in the DRI. It's a huge amount, and perhaps you will see in the future the 100% DRI companies, or the typically 80-ton DRI companies, will try to use more scrap. That will affect the foundry market. In the next decade, there will be a change. We can have a next slide. So when you work in a foundry or a steel plant, but in a foundry, this is the topic today, you are very well aware of the chemical composition of the different raw materials. You have classified raw materials, E3, E2, old thick, new thick, shredded material, turnings, and you can use rather simple algorithms to get a good idea of the chemical content. What is also important is to know something about the distribution. How sure can we be about the chemical composition? What is the standard deviation for the chemical composition of the copper composition, for example, in E306? It says here 0.2 for E3, but if you charge a number of tons, how much will it vary? The left curves there, you have normal distributions. These are from a rather small electric arc furnace where you have 7 different steel types produced. And you look at an element, it could be nickel, copper, chromium, anything. And you see that depending on the recipe, you will have a distribution. So you could easily say that, okay, this is the distribution that comes from the raw materials. But actually, some of the distribution, some of the variation comes from the variation in how the baskets are loaded in the furnace. But having this under control, is important for tramp element control, having good idea of the copper nickel content if that's limiting, and if you want to use alloys in scrap to get the right alloy content, not too much nickel, but use nickel in scrap rather than nickel in alloys. So this is really important. We can have the next slide. If you look at the company and you look at the basic functions in a company, you have sales and marketing, research and development, and production and distributions. According to many business scientists, these are the three main activities. And you have them with your suppliers, you have them in your customers, and you have them in your own company. And for example, research and development in a foundry could be one person, or it could be one person part-time. But you always need to have a research and development, otherwise you're dead within a few years. You have a sales and marketing, again, that could be one person, or it could be a department of 30 persons or 100 persons or something like that. It doesn't matter really. It's the same functions that you need in a company. And depending on your customer's requests and what your supplier can supply, you have to create your world, you create your production. So what do the customers request at the moment? Well, the customers, of course, they request a certain tensile strength and ductility and whatever, but they also request a low carbon footprint of the product because their products are valued according to their environmental footprint. And this sudden request, well, we felt it before, but suddenly it's become very clear that they mean business. And just the other day, we had a bombshell detonating in Sweden, where a new steel plant was announced to produce some 2.5 million ton within the next 5 years, and using hydrogen for reduction of iron ore, but around 40 to 60% scrap. That will change the entire scene up in northern Sweden. They will take another million ton of scrap, good scrap, in order to produce something. And the basic idea, the basic demand came from Volkswagen, obviously. So we have new types of product requests coming in that we have to act towards and act on. And another thing that is changing is the emission allowances. And it hasn't really mattered before, but now when the emission allowances are quite high and we don't know how much they will raise, then this will be an issue, and it will affect the steel makers, and they will suddenly start to request anything that can help them keep down their costs for CO2 emissions. And that could be buying scrap. So be prepared. What you really have to do is to work in a proactive manner, understanding what is going on and preparing your production for that. And in this sketch here, we have the basic production figures there in orange going to green. And you have the procurement function, you have the production planning, and you have the monitoring production optimization system there. And that is really a central function in a company to take care of the of being agile to take care of the changing world. We can have the next picture, please. So if you look at just the monitoring part here, you can divide it into 3 parts: production evaluation, update production system, and production management issues. The production evaluation, that is really seeing that, are we loading our material in the right way, or do we have liberty for the people on the scrapyard to do a little bit what they want? Do we really have a good view on the scrap quality, and do we pay the right price for the scrap? Do we have the right slag practice? And the slag practice must change with the scrap quality or the raw material quality. Do we have the recipe quality? Do we have the casting quality we need? Carbon footprint, of course, that is extremely important now when the customers looking at it. And do we have the right timekeeping? And of course, other things that we could look at in the production evaluation. And then when we understand, have a good view on your production, you could start looking at updating your production system. Do we have the right instructions for the people loading the baskets on the scrapyard? Do we have the right demands for our different scrap types, and do we use the right data when we do optimization? Do we understand the value of different scrap types? Expensive is not always expensive, cheap is not always cheap. So do we have optimal recipes for our production? Do we have the right instructions for our furnace production personnel? Do we do it right? We have here very close connection between buying the right material and using it in the right way, especially when it comes to avoiding inclusions and things like that. Maintenance instructions, data sampling and storage, evaluation routines. And having updated your production system, you can make decisions about an optimal inventory size, input to raw material procurement, what should we buy, and input to production planning, and of course reporting to the top management, which could be a board of directors on the other side of the world, or the boss living next door to the foundry. Doesn't really matter. It's the same business. And at the end, it affects the operations, the procurement, the equipment maintenance, the system maintenance, production planning, and the actually production in the different processes. Next slide, please. So what we do when we do this work with this at Cobalda, we have a system we call ROMAT-STAT for the evaluation, and we have another system, ROMAT-MIX, but for really calculating recipes and things like that. But that is not the important thing. With the ROMAT-STAT, you can do the production evaluation. You have a small picture there. It's actually something we've measured. It's the copper content that we could actually, with different statistical methods, better and better understand what is the copper content of different raw materials. Methods have evolved during the last decade. And we can update the production system that is doing the right, having the right upper and lower limits, and getting the price efficient recipes to do this. So, but again, the tools are not the important thing. You could do wonders in Excel. There are a number of tools like ours that you could use. It doesn't really matter. The most important thing is training the people to working in this way and having a management understanding the importance of raw materials and the vigilance to understand that now everything is changing, and it's changing rapidly. We thought we had a rather slow movement ahead, but it's not. The next slide, please. What we say in the first picture of our homepage is what would a 1% reduction in raw material cost mean for you? And the raw material cost is normally a very high part of your production cost. And what we say is that you can always cut 1% of the raw material cost easily if you go from a very non-structured way of working to a very structured way of working. It could be 2, 5. The worst I've seen was 10% we could do. But you could always do 1%. So if you're thinking of how much should we put in, how much time, how much effort should we put in, take 1% of your raw material turnaround and look at that and see, is this enough to work for? Normally it is. So I wish you all good luck in the future with this, with your raw material procurement and follow up. Thank you for your attention.
Thank you very much, everyone. Very nice presentations. Thank you, Johan. Thank you, Rutger. Thank you, Lucian. So now we are ready to take the next steps. And I think there are 2 questions in the chat. Stefan, you are in charge of the chat. Should we take that before the group discussion?
Well, actually, I don't see any questions in the chat.
Okay.
Maybe they are addressed